done, they're going to be standing more on the floors because they have something to do to show you out front here. So this one is the autonomous guided vehicle using a robotic arm. If any of you need, we have programs, so if you want to put your hand up if you need a program, one of our, Brittany will come around and bring one to you if you need it. But gentlemen, you can come up to the front and start your presentation. My apologies. John, I gave you a promotion apparently. Alumni Association, not the Board of Governors. Sorry about that.
Wow, I am excited instead of nervous. So, good morning all. My name is Yash Soni.
Hello everyone, I am Deual Patel. We are second year robotics students from Sinclair College, and we are also working as a student researchers with the college research and development team.
So today we are going to present our research project, which is based on an proof of concept, in which we are going to use an autonomous guided vehicle, in short AGV, with an robotic arm and the vision system mounted on it, in order to perform a vision-based smart operation. So, highlights of our projects are an AGV named Boxer, and a robotic arm which name is UR10E, then a pair of Robotics cameras, a Picket 3D vision system, and the part tracking technology. So, our project is divided into 3 phases, in which we have already achieved the first two phases. In first phases, we have mastered the mapping feature of the AGV, and we have done electrical integration of the robotic arm and the AGV. In phase 2, we have done we have integrated a 3D vision system with a robotic arm in order to perform any operation. And in phase 3, we are going to integrate the path tracking technology with an AGV. So now here to my friend Deual.
So the primary objective of this project is to perform the vision-based operations with the help of a mobile platform. So that's why we are using an autonomous vehicle. So the AGV that we are using, it basically operates on the robot operating system that is ROS. It is equipped with the cameras and a bunch of sensors like LiDAR, sonar, and odometry as well. It also has an inbuilt ARC computer through which we can do the mapping of a particular area. So this image shows the visualization of the ARC software where the mapping of a particular area is done. With the help of this software, we can create predefined routes through which we can command the AGV to navigate itself autonomously. The UR integration into the robot is done in such a way that it utilizes the power with the help of the batteries that is inbuilt, that are basically located inside the AGV. Now coming to the phase 2 of the project, we have integrated a 3D vision system with a robotic arm. The 3D vision system basically identifies the coordinates of an object that are located in the 3D space, and it will sense the coordinates to the robot, through which a robot can later on program itself and through the task that we want to perform. So this is a basic setup of our vision system, and the blue markers which is shown over here, it basically shows the objects that are being currently scanned by the vision system. We will also demonstrate a simple pick and place system at the end of the presentation.
So now, vision, all operation will go fine as long as the robot and the picket system remain calibrated. So, but sometimes it can be happen that robot can be altered or the vision system can be altered even a little bit. The whole operation can be malfunction. So here comes the picket part tracking technology in the picture. In this technology, the part tracking technology will send the coordinates of the vision system or the workstation constantly to the AGV. So AGV can correct itself by giving itself command to as a feedback loop. So in this technology, there are three main components. The first is pair of radix camera, then binary markers, and another is the part tracker software. So radix camera take the images of these binary markers which represent a specific number. For this instance, 5, 6, and 7. And part tracker, and these are transferred to the part tracker software. And in part tracker software, the coordinates of these markers are automatically calculated. So now what we will do, we will put those markers on the AGV and one on the workstation. So whenever those marker come in the radar of the radix cameras, it will calculate coordinates and it will start a constant feedback loop for the AGV, so it can correct itself. So this is how coordinates looks like. The one is on the left there is a setup where the markers are placed, and on the right there is a part tracker software where you can see the coordinates calculated by the part tracking software. So in the case, even if there is inaccuracy for the AGV, with the part tracking software we can correct that and achieve our problem without malfunction of the operation.
Sorry, I think something malfunction. We actually placed it wrong location, that's why.
That was actually a drop of position, but we forgot to arrange the object in order to place it. So now one.
So we have currently taught these three objects with the help of the vision cameras. We have taught the pickup and drop locations where the robot will automatically jog itself with the help of the 3D, with the help of the coordinates of the objects that it gets with the 3D vision cameras. It will pick the objects and it will put it at the drop location. Maybe due to some kind of error in calibration or lighting, it didn't pick that locate properly.
So that is where the third part comes in. The part. So okay, now it's done properly. So it was maybe because of lighting, because when we trained the objects, the lighting were different.
So this is a very innovative concept where we have merged the three different segments of technologies in an exclusive way. This proof of concept can be applied in the industries like automobiles or aviation, where the different parts assembling can be handled. We can also use this concept in the warehouses as well, where we can utilize this project in handling material handling and storage, and we can even use these in the food industries to sort the vegetables and fruits. Thank you.
Thank you, gentlemen. We're going to give them a moment. They're going to move that out of the way. If we have our next group to come up, Bethany from Interact, please. Oh, sorry. Bethany's getting ready while we have questions. The microphone is there for you, Sandy, if you want to go.
Is it on? Okay. Hello. Thank you. That was very interesting. I'm very familiar with AGVs. I was a control supervisor in the previous role. But I did have a question. If you could just, I have two, but I'm going to ask the question about how do you account for depth of pickup to accommodate fluctuations in different donnages as our parts come in? So how does this account for that?
It is a 3D vision system through which it can locate a particular object in the 3D space. So when we train the particular object with the vision system, it shows the different points that has been scanned, and we taught the gripper to exactly pick that particular part by defining that points. So that is how the 3D vision system is basically defining the depth and all that things.